Okay, good afternoon, everybody. Thanks for joining the seminar. Today, I'm going to talk about a project that I had meant to work on since a couple of years, and some of you might have seen some of the introductory slides before, at least the motivation of what I want to do. And this spring, it so happened that I had a research sabbatical in which I had a lot of time and finally managed to sort of get the results I had been looking for since a couple of years. So the title of this work is Informative Explanations Only Exist for Simple Functions. And this is joint work with many people in my team, pretty much everybody, I would say. Formally, it's about one paper, which and the authors you can see on the slide here as well. But I guess it is also a result of many discussions we've had during the last couple of, maybe even years, I would say. And now I can, okay. Okay, so my motivation to work on explainable machine learning very much comes from impacts of machine learning to society, and in particular also looking at regulation. So most of you would know that the EU has passed the AI Act last year, and it is now being implemented step by step in all the member countries of the EU. And the AI Act regulates the use of artificial intelligence by companies in the European Union. And in particular, it regulates the use of high-risk artificial intelligence. And like speaking a bit sloppy, high-risk systems are systems that heavily influence people's lives. So it might be university admission, or it might be credit, like credit assignment. Like whenever you have AI tools that take important decisions about a person's life, then this is considered high risk. Because if the thing goes really wrong, society will be in trouble. And within the AI Act, there are several places which talk about explanation, but the most explicit one is Article 86, which says there is a right to explanation of individual decision making. So if you are the subject, like you apply for a loan at the bank and the bank tells you, sorry, you didn't get the loan, then you're supposed to be able to ask, why didn't I get the loan? And the bank is supposed to give you an answer. Now, obviously, in such a scenario, the bank cannot just invent any explanation. I mean, this would be sort of stupid if the AI Act would be satisfied with such an explanation. So what we would like to have in such a case is that the explanation is reliable, whatever that means, trustworthy, true, whatever that means. So, but definitely there might be some attributes that you would like to give to the explanation that prevent the bank from just making it up. Okay, and this is what I'm interested in. And so what can we prove about explainable machine learning? So the setup I want to consider in my talk is a very simple one, and this is comes from the applications of the AI Act, which very often have tabular data, like university admission, credit lending, and so on. You describe each individual person by lots of attributes, like what is your age, what is your income, how many kids do you have, I don't know, where do you live, and so on. So we have tabular data, and definitely I don't talk about text data in this talk. So it's not about ChatGPT, it's all about tabular data. And we assume it's high-dimensional data. We have lots of features of each person. And then we assume there's a complex prediction function that the bank maybe uses to assign my credit or not. I don't know the function, but it might be, I expect it's maybe not a linear model, but something very complex. So it's not interpretable as a whole. And then what our community has suggested many times is that in such a situation, the bank could provide me a local post hoc explanation of the prediction at my particular case. So looking here, f is the decision function. X0 is now always going to be the point at which I want where I want to get the decision explained. And so like in this image, we have data points, we have a decision surface, we have this yellow guy, and we ask, why did this yellow guy end up on this side of the decision surface? And then maybe the bank returns some, I don't know, feature important measure, histograms or whatever it returns. And I always want to abstractly denote the explanation by this curly epsilon of f of x0. And it can be feature attributions, it could be a gradient, it could also be something completely different, an anchor or a counterfactual. Okay. Now, as I said, I'm looking for theoretical guarantees. And of course, like if you start working in this field, you open the papers and you try to figure out what theoretical guarantees do exist, and you will find that there are lots of guarantees in simple settings. So if the bank uses a linear model and I don't know, you apply a gradient explanation, then probably the gradient explanation is going to tell you something important about your function. Or here in this example, if you have a very simple data set, say a mixture of two Gaussians, and only feature 1 is important, and feature 2 is completely non-important, and you ask whatever reasonable explanation algorithm which feature is more important, all of them will return that the first feature is important, and the others are not. So in these simple situations, guarantees exist, and they exist for lots of algorithms in lots of simple flavors. However, my feeling is that this is not what we are looking for. I mean, this is nice and it's reassuring. If it wouldn't be true, we could stop here. But in fact, we are not interested in this simple situation. We are interested in this complex situation. I mean, the very reason for which we design explanations is that we think there's a very complex function, and now the bank is still supposed to give me some explanation. Okay, and so many people, including ourselves, have started to look into guarantees. What kind of guarantees would we maybe able to prove in such a complex setting if we don't have a linear function or an additive model or something like that? And then you start trying to prove stuff, you start trying to formalize whatever you want to prove, and you always, somehow you don't get it, right? And the gut feeling you get is, I mean, of course, there's no ground truth in many cases, like as in the credit lending. I mean, there is no ground truth why this neural network really assigned this value and not the other one. There is a high amount of ambiguity depending on which explanation algorithm you ask or how you choose the parameters or the distance function or whatever, you will get different results. And this is often very subtle, so it's not like if you just change something very minor, you get different explanations. And so the longer you try to prove guarantees in this scenario, the more you maybe start realizing that it might not be so simple. Okay, and then you can, I mean, we had sort of empirical studies. We also looked into auditing. Then we thought maybe, well, if you can't prove a guarantee, maybe we can try to audit in hindsight, and all these things somehow don't work. Okay, and then you start wondering, and eventually we started to discuss a conjecture that it might be impossible to prove a guarantee in a complex setting. And of course, like there are different ways in which you could say it is not possible, but here's one way, one conjecture that's been floating around in our group since at least a year, or maybe, I guess, probably even 2. And informally, the conjecture says the following. If an explanation algorithm can provide useful explanations for most data points, then the decision function has to be simple already. Okay? So looking at the other way around, taking the contrapositive, it says if the decision function is not simple, so we suspect the bank uses a neural network, the decision function is not simple, well then, if this conjecture is true, it simply is impossible that the bank would be able to provide useful explanations for all data points. Okay? And if this conjecture is true, it is somewhat a devastating statement, right? Because, I mean, we come up with the idea that we have a very complex function and we want to explain it, but now we say, well, it somehow doesn't seem to work in this scenario. Now, of course, this is very informal, and it all depends on what is useful and what is simple and what do we mean by most data points and so on, right? So this is the informal conjecture, and now we need to try to make it formal. And so the most important notion that we need to get right is this notion of usefulness. And so the first idea everybody would have, at least everybody who knows the literature in this field would say, oh, probably useful is something like maybe faithful. So a faithful explanation typically is, I mean, there exist many different flavors, but on a high level, faithful always says, well, the explanation is supposed to at least depend on the underlying function. It should maybe also depend on the data point at which we're asking. So it's something that is not invented. This is what faithful is supposed to say. So you start trying to prove the conjecture for faithful, but then you realize that this is not the correct notion. And here are 2 examples which illustrate that. So the first one is a really stupid example. It's what we call the tautological explanation. So we could say we want to ask for an explanation at a function f at data point x0, and we just say, well, the explanation is f of x0, which is, of course, stupid. So essentially, we ask the bank, why didn't I get the credit? And the bank just says, well, you simply didn't get the credit. So they don't tell us anything new, they just repeat what we already know. Of course, intuitively, this is not at all what we would consider an explanation. It is, I mean, the bank doesn't tell us anything we didn't know before. But like if you start applying all these notions of faithfulness, it is as faithful as it could be. It depends on the function, it depends on the data point, like all its properties sort of are true to a certain degree, but they are completely meaningless. Okay, so faithful obviously is not the only thing we might want to have. And another observation is a different one. Namely, there might exist functions that do not seem to have something like a useful explanation. And an example would be something like a random function. So just assume, I mean, for the sake of the example, it's a discrete space and you just have like you randomly toss coins for each data point, whether the function is plus or minus 1. You fix it and this is your decision function. And now you ask, why did this function assign, I don't know, minus 1 to this data point? Of course, you can apply, I don't know, SHAP to this thing and it's going to spit out a value. But this value is not going to tell you anything that you wouldn't know. It's probably giving you some mean, which is sort of the same kind of value for all data points. And if it doesn't, it is just up to some noise that you have in your function. So somehow there is a mechanism here that this function seems to be unexplainable. Or at least, I mean, the SHAP explanation might still be correct in the sense, I don't know, it looks at all the correct conditional expectations or so, but it doesn't tell us something. Okay, and so what we're looking for is something else. So on a very high level, what we're looking for is we're looking for a definition, first of all, for a definition that is general in the sense that it's not just one definition that works, I don't know, for SHAP, and then we need a different one for gradients, and then a third one for counterfactuals. We want a general mechanism. And for now, we only have a sort of modest goal. We want to distinguish useful from useless. So we do not want to measure how useful an explanation is or for what purpose an explanation might be useful. We just want to say, is it useful or is it completely useless? And the argument is going to be, if an explanation in our framework is going to be useless, you cannot use it for any purpose. So, I mean, no matter what you want to do with the explanation later on, it doesn't help you in that purpose. And so this sort of hopefully helps us to get away from this discussion, what is the purpose of your explanation in the first place? Okay, and now here's the general idea. So consider the following setting. So we're the bank customer. The bank tells us already you didn't get the credit. So this is the decision. So abstractly, we know the decision function, like the value of the function at the data point we're interested in. This is what we know before we ask for an explanation. And now we ask for an explanation. Why didn't we get the credit? And so we receive an explanation. Can be anything. And now we're asking, what have we learned through the explanation in addition to what we had already known before? Right? And in like already thinking about this example, for example, for the tautological explanation, we didn't learn anything. And probably for the random function, we also didn't learn anything interesting. So this is what we're trying to head for. And now we try to make it a bit more formal. Okay, so we want to argue about what we learned through an explanation. So we probably also need to talk abstractly about the background knowledge that we already have. And as so often in machine learning theory, the background knowledge in this case is encoded in a function space. So we assume we know that the bank uses a certain function space, say all neural networks or all random forests. So it can be really a huge space, but there needs to be one. Or you could probably you could also look at the space of all functions, but then, yeah, okay. But sort of you need to encode what is your prior knowledge. It's curly F. And now we look at, so here we have an image space of all functions. So these are all the potential functions the bank could have been using. And now we look at the blue function class F predict, which consists of all functions in our space, which agree in their prediction with the prediction that we have gotten. So like the bank tells us you don't get the credit, and there are like many, many functions in the space which all don't give us the credit. And this is the space of the blue functions. So after receiving the credit decision, we already can rule out some function. Like any function that would have given me the credit is not the one the bank uses. So we can restrict the space and know after we receive the prediction, we know the function lives in this blue space. Now we ask for an explanation and we receive the explanation. And now what we define is now a potentially smaller space, namely all those functions which not only agree with our function in the prediction, but also in the explanation. So, for example, the bank tells me the income was the most important thing. So the yellow functions are all other functions in the space that don't give me the credit, and where the explanation would be the income is the important feature. So formally, it's all functions in my space which agree in that prediction with the one I got, and whose explanation on point x0 is the same as the explanation we received. Okay. And now we can already start thinking about where we're heading at. So what we wanted to say is, did we learn anything by receiving the explanation? And so looking at these images, so when did we learn anything? Or maybe when didn't we learn anything? We definitely didn't learn anything if the yellow and the blue function space are identical. So for example, all functions get exactly the same kind of explanation. Then the yellow and the blue function space coincide, and there's not a single function that I could rule out after receiving the explanation. So the explanation was completely meaningless. And the other way around, we now want to say an explanation is maybe not meaningless if the blue and the yellow space are not identical. Okay. And now we have two definitions that we want to make there are different ways of measuring in which way the blue and the yellow function space agree. So the first definition is, we say an explanation is non-trivial if the blue function space is strictly larger than the yellow function space, just in the set theoretic difference. So there exists at least one function in the blue space that we can rule out once we have seen the yellow explanation. Okay, so this is sort of the first obvious thing. And we are going to see that it's still a pretty weak notion of information. This is why we just call it non-trivial. And then we're going to have a stronger notion in which we just measure the difference between the blue and the yellow function space in a different measure. So we now say an explanation is informative. And now we compare the Rademacher complexities of the blue function space and the yellow function space. And we say the explanation is informative if the Rademacher complexity of the blue function space is strictly larger than the one of the yellow function space. And to a certain degree, this is supposed to say that we not can only rule out one single function, but there is sort of a substantial amount of functions that we can rule out. And we are going to see in a minute lots of examples, and then we're also going to see what the difference is here between these two notions and why we need the second one. Now, before I continue, I wanted to ask whether everybody is still with me, and in particular also whether everybody knows what the Rademacher complexity is, or whether you would like me to explain it. I'm happy to do so, just if everybody knows it, I'm not going to do it. So would somebody like me to explain Rademacher complexity? Then you need to speak now, because I don't see all your images. Okay. If not, then I just assume that everybody knows it. And if someone would like to ask a question now before I go into the example, that might also be a good point in time. But you can also keep your questions to later if you like.
Actually, Ulrike?
Yeah.
I was wondering, so in this inequality with the Rademacher complexity, there's no epsilon, it's just strict inequality.
Yeah, exactly. So this is what I was referring to earlier. We just want to distinguish useful from useless. We do not want to measure how useful it is. The next step would later on be to say, well, how much difference do we actually have? And is the difference larger than something trivial? But yeah, that would be the next step. But indeed.
Can I ask, so the notion of explanation here is only about the final function, not why it is that was learned or what training data. Okay.
Yeah, that's a very good observation. So the scenario we have is someone gives us a function, and we do not care at all where it comes from. The bank just gives it, or God gives it, or whatever. Like someone makes a decision with this function. We don't care where it comes from. And we also, in particular, do not assume we know anything about the training data or the distribution or anything. It's really completely uninformative in this, or we don't know anything about this. Agnostic, I think. Okay. So let's maybe look at a couple of examples. So the first thing is, I started with this example of the tautological explanation where we just say, well, the explanation is f of x. So then what we have is the yellow and the blue function space are exactly the same. And to see that, I maybe go back to the definition. So the blue space is all functions who agree on their prediction. The yellow is the one who additionally also agree on the explanation, and now the explanation is the same as the prediction, so obviously these two spaces are the same. So in this sense, and this is here this definition, if the spaces are the same, then the explanation is trivial. Okay. So this is good in the sense that we didn't want the tautological explanation to be interesting in some way. And if it's trivial, it's also not informative in any case. Let's maybe look at the simple example where everybody looks first, the linear function. So assume now we have linear functions and say we apply a gradient explanation. So you would imagine a gradient explanation is quite informative about a linear function because once you know the gradient, you know everything. So, and now we want to see whether this is also the outcome. So we look at, first of all, the space f predict, which consists, like I know the function value f of x. Now I look at what are all the other functions in the space that receive the same function value f of x. And this is the blue space f predict. There will be many linear functions, which sort of also don't give me the credit. And now I look at f explain, which consists of all functions which give me the same prediction. And now I get a gradient explanation who have the same gradient as my function. Okay, now I know one point, I know the gradient, I know the function. So the space f explain here just consists of one single function. And this is perfect. So essentially I went from a space with many, many functions by receiving the explanation to a space of one function. So intuitively we would say, well, it can't be more informative than that. After the explanation, I don't know the function. And this is also the outcome. So obviously it's non-trivial because the yellow space is smaller than the blue one, but it's also informative because the Rademacher complexity of a set which just has one function is 0, and the one of the blue function space is larger than 0, so it's different, so the explanation is informative. Makes sense. Okay. But now let's look at a different example, which is maybe more interesting. And this example now consists of what I call weakly linear functions. I don't know whether this is a perfect English word, but so what I mean by these functions is, it is on a high level, it's like on a global scale, it's a linear function, but I allow to add tiny little noise of size epsilon to the function. So essentially it's a function, it's a linear function plus noise of size up to epsilon in such a way that it's still differentiable because we want to apply gradient explanations. Okay. So now we want to look at the space of all these weakly linear functions. And we again take gradient explanations. And now if you start thinking about it, you would maybe or hopefully come to the conclusion that gradients might not be informative in this scenario. So what would you like to learn? So you receive the point, okay, you know that your function goes to the data point, but now by receiving the explanation, you would maybe want to restrict the direction of the linear function. So you would like to say by receiving the explanation, maybe the linear function is only in this part of the space, but it can't do something completely different. But now the point is, like looking at the gradient of the function that we have, it is completely non-informative about the general direction of this linear function. I mean, you can just wiggle as you like, and you can have any gradient. Like locally at this data point, you can have any gradient that you like, yet still globally the function does whatever you like to do. And so what happens now is interesting. So what we can see is the gradient explanation is non-trivial, because we can rule out some functions. Maybe we can rule out all functions that do not exactly have the same gradient. However, this is sort of not interesting. I mean, they're like, essentially you just rule out functions by how they behave, like what is the wiggle that they have at your data point. So you can definitely rule out functions, but sort of nothing interesting. Because on a high level, what happens is you still have all possible linear directions that you could possibly have in your function space. And you can then also formally prove that the Rademacher complexity of both of these spaces, whether you fix the gradient or not, is the same. Because there is no, and like intuitively what happens, like if in the Rademacher complexity, what do? You distribute lots of functions on your space with different labels. And if there is some labeling that can realize, or if there's a linear function that can realize a particular labeling in this space, you can also realize it in this space. because there's no, like, knowing the gradient of the function at the point doesn't really restrict the possibility of what the function can do. And so this is, but yet it is still an example where our definitions sort of work, because what we wanted to say is it is probably not informative, because there's nothing that we could conclude from this definition, from this explanation. Okay, so far so good. Okay. And if we believe, okay, and now you can come up with millions of examples, and you will always, I mean, like we tried many, many examples, and we always found that our intuitive notion of what an informative explanation might be tends to agree with what we see, according to our definition. So now let's try to apply this more generally. So now say we have a neural network. We train a neural network, and simply for the sake of the argument, assume the neural network ends up in a differentiable function. So maybe it's ReLU, but sort of smooth in a way, because we don't want to now argue about, I don't know, pieces in parts of the space where it's not differentiable. So for now, let's assume we look at the space of all differentiable functions. And intuitively think about this is all the functions that your neural network could realize. We are on a space in RD, and we just assume we have a positive density and no point masses. Okay. And then you can now prove for all functions in this function space and for all points on which you could query, the gradient explanation, which takes the function and the point and returns the actual gradient of the function at this data point, is not informative. Okay. So maybe digest this a bit. So we look at all differentiable functions. It's a huge space. Now we say, well, if someone tells you the gradient of a function, you can't draw any information from the gradient. And on a very, very high level, I'll show you the proof in a second, but sort of the proof idea is like or maybe let's even do it without a figure. So if you know, like you have all possibilities of all differentiable functions. Now, the situation is a bit like in the weakly linear functions. If someone tells you what is the gradient at this particular data point, it doesn't restrict at all what the function's behavior could be in any other part of the space, not on a single. So no matter which other data point you pick in your space, if you know the gradient at your original data point, you don't have any clue what happens at this other data point. And on a high level, this is why it's not informative. Now the proof, in fact, like if you have a math background, it's sort of the obvious proof. I think it's not difficult at all. So maybe what we do is, I mean, we first fix a Rademacher sample. So you need to sample some points and you need to sample some random labels. And now you try to find the function that optimizes this Rademacher quantity that you need to optimize. And say it's a blue function. You fix it. Say that's the blue function we have here. And at your given data point x0, it takes the value that you prescribe. Okay. And now we want to see what happens with the yellow functions. And now we do the following. So once we have the blue and orange points are our Rademacher samples, what we now do is we choose a ball that is so small that none of the Rademacher samples is included in the ball. And now we say, well, in this ball, we can change the function as we like. I mean, we keep it still differentiable, but what we now ensure is we make sure that the gradient of the new function agrees with the original function, with the one we're looking for. And everything happens in a differentiable way, so we don't sort of step out of our function space. But outside of this gray ball, we just do what the original function has been doing. And you can always do that because there exists, I mean, the ball might be tiny, but it exists, and we don't have any restriction, for example, on the curvature of our function. So we can always do this kind of adaptation. And so what you then can see, so you choose this ball that doesn't take any Rademacher points. Within this ball, you might modify the function such that it now lives in the explain class, so it has the correct derivative or gradient at your data point. And then obviously, like if you sort of try to see how well does this blue function and the yellow function, sort of how well do they perform on this given Rademacher sample way, they give exactly the same decision. So they perform exactly the same. And so then you can conclude for this particular Rademacher sample, like the two spaces behave the same. Okay, now you need to take expectations and need to be a bit more careful in doing that. But there's nothing really difficult or unexpected in this proof. Okay, so here is again my sort of blunt way of stating it. And I think this is a picture that simply one might keep in mind and maybe even forget about the proof. So we have a data point, and now we receive the explanation, which is the gradient. This explanation doesn't tell us anything about what the function does at any other point in the space, if functions can be arbitrary differentiable functions. Okay, now looking at this proof, you might immediately realize, maybe there is a way to save that, namely, or to make it better. Namely, what we did in this proof is we had an arbitrarily small gray ball in which we needed to change the direction of the function, and we might need to introduce a very high curvature to be able to do that. So what you can now do is you can say, well, what if we don't start with all differentiable functions, but we start with differentiable functions which have a bounded curvature? So formally what we do is we bound the gradient of the function by a constant, and we also have some Lipschitz condition on the gradient. So intuitively, we bound the curvature of the function. Once we do that, then the gradient explanation does become informative. And what happens is now, like, here's our data point. We know the red line is sort of the gradient. Now there exists a gray ball of a positive radius, and I can already specify this radius once I know these alpha and beta here, such that within this gray ball, the red function and any other function that has the same derivative sort of behave the same up to some tiny epsilon. So now if we have Rademacher samples which fall in this ball, then the yellow and the blue functions sort of can achieve the same kind of things. But this means, like, it does make a difference whether I fix the gradient here or whether I don't fix it. So if I don't fix the gradient, as it is the case in the blue function space, then, sorry, I said it wrong previously. So if I'm in the blue function space, I can have all arbitrary gradients in this image, and like I can achieve many more labelings than if I fix my gradient to the yellow one that I have here. So on this function space, gradient explanations are informative. Okay, now this was the first sort of simplest explanation algorithm we've been looking. So maybe let's step back. So we did make this definition about when is a gradient. Maybe go back. Here we sort of defined when is an explanation informative, namely if it helps us restrict the function space from the blue one to the yellow one in terms of Rademacher complexity. And we now saw, if we look at all differentiable functions, gradient explanations are not informative. If you look at a smaller space of more simple functions, namely with a bounded curvature, it becomes informative. And this is now a pattern that we now see for many other explanation algorithms as well. So, like, if you want to be critical, you could say, well, I mean, for gradients, it's sort of obvious. We look at this very, very, very local property. Of course, if we don't sort of restrict what happens, it's not going to be informative. Okay, now you can look at SHAP, because SHAP is an algorithm that is not as local as a gradient. So, I mean, it at least looks at conditional or marginal expectations, depending on what version you're looking at. So definitely you can't just say it depends just on what happens within a tiny region, and we can completely ignore what happens outside. What is going to happen is a similar picture, and maybe that's a bit surprising. So now the notion of simplicity, like previously we looked at gradient explanations and the curvature. Now we look at decision trees, and we look at the depth of the tree. So we say, if we have the space of trees with arbitrary depths, which we call T infinity, so the depths can be, I mean, of course it's finite but not bounded, then what we're going to find is SHAP is not informative. Whereas if we look at trees of a bounded depth, up to depth k, then the SHAP algorithm is informative. And now I don't really want to go through the whole proof. It's a bit more technical, but the intuition is the following. So again, we fix a Rademacher sample of points like random points and their labels, orange or blue. We have the point at which we have the explanation. And now you want to say, given all functions in the predict space, what would be the best labeling of these Rademacher points? Okay, and you look at this, and then you look at the f-explain case. So these are all functions. You look at all possible functions that you can realize on these data points, but sort of fixing the Shep values. So you say, I only look at functions whose Shep values agree with x0. And what you now have to do is, like, if you're just in fpredict, sort of you can, in principle, and you have infinitely deep trees, you can dedicate a single leaf to all these points, and you can do whatever you like. However, if your decision tree has a bounded depth, you might be able to dedicate some leaves to these Rademacher points. But then what you also need is you need to dedicate some leaves, and I don't want to explain how it works really, to make sure that the Shep values are the correct ones. So intuitively, the Shep values have to do something with the expectation. So you can fiddle around with the function at different places, but then somewhere else you need to have some kind of a region where you set the function to a value such that overall expectations are met. And you need to dedicate some leaves there. So you have less possibilities to fit Rademacher points. Okay, so this is the case of Shep. And I know it's not very satisfactory because one would need to spend more time with the proof, but I don't have that time. Because I still want to look at counterfactuals. Because counterfactuals are currently in the discussion about regulation are often treated as sort of the most promising candidate. I mean, obviously a bank wouldn't give me Shep values. I mean, that somehow what should I do with a Shep value? So many people say the bank should give me a counterfactual explanation. And so what is a counterfactual explanation? So given my data point, the yellow one, I ask for an explanation. And the counterfactual explanation is a different data point on which receives the different decision. For example, I didn't get the credit, and then the counterfactual would say, well, but if you would earn 2,000 euros more per month, you would get the credit. So the bank reveals one data point. So I sit in the blue space, I didn't get the credit, and the bank reveals another data point somewhere in the space, which says, well, if you would be this guy, then you would get the credit. Okay, now there are different mechanisms and algorithms by which you can derive these counterfactual explanations. And now we want to make a distinction which is not typically done in the literature. We want to distinguish between strong and weak counterfactual explanations. A strong counterfactual explanation is the one that sort of was advocated for in the very original paper for counterfactuals, namely the closest point that sits on the other side of the decision surface. So you minimize on all points what is the closest one, and this is your counterfactual. This is what we call a strong counterfactual. And we will see that strong counterfactual explanations are in fact informative, because if we receive a strong counterfactual, we know that everybody in this blue circle here, which has the radius, which is the distance to the counterfactual, we know everybody in this blue region has the same level as I have. And this definitely is informative, also in this Rademacher notion. What happens in practice, though, is people, of course, they don't guarantee that we get the closest one. What people do is, if they want to find a counterfactual, is they run some kind of gradient descent. I mean, you start at the point where you are, you run a gradient descent until you're on somewhere on the other side. You do some steps. It's a greedy algorithm typically, and then you find a counterfactual. And this is what we call a weak counterfactual. So a weak counterfactual is just some point that sits somewhere on the other side of the decision surface. It could be this guy if I maybe just walk in this direction, which is still fine. It could also be this guy because I don't know, the step size in my greedy algorithm was a bit larger, so I make a big step, so I'm very far in the red region. It could even be this guy, so maybe my step size was so large that I ended up here and not here. So whatever happens in this algorithm. So all these are weak counterfactuals. And now intuitively you can already guess what happens, namely weak counterfactuals are again not informative. If I have a weak counterfactual and the bank tells me, well, here on this guy, you would get the credit. Okay, I know this is the one other data point or the other label that I receive, but it has probability mass 0. So, and everywhere else in the space, I know nothing. I really know nothing. And this is, I later have, or maybe I want to show you this illustration here. And this is really what happens in practice. So for example, like this is just a simple simulation. I don't know some credit data. Here you have the age and the education level. And then the question is, do you get the credit or not? It's real some data set we downloaded. This is the data point, this is the counterfactual, and this is a random forest. And the random forest, you already see it sort of, I mean, this is not what you would expect here, right? I mean, here you get the counterfactual, but for example, if the age is a bit larger, again, you don't get the credit. Or here, your education level, if it's a bit larger, you get the credit, but all of a sudden, if it's even larger, you don't get it. So somehow, I mean, you could now say this is a stupid classifier, but I mean, you don't know what are all the other data dimensions. There might be 50 more features. There might also be correlations in your data set. So it is completely typical that a random forest looks like this, unless you take any countermeasures. But typically, this is how it looks like, even though people don't expect that. Okay. So I mean, and I don't have time to go more into this. So the general pattern is we see in many explanation algorithms, if you do not restrict your function space, like explanations are not informative, they do become informative as soon as the function space is a bit more simple. And now I would like just to end with a general discussion what it means. So in very plain language, it means if we do not know anything about how complex the function is, no matter which explanation I look at from a large class of explanations, they do not convey any information whatsoever. They're completely void of information. They don't tell me anything. And it applies to pretty much all algorithms. It applies to neural networks, to random forests, to boosting, and to all algorithms like counterfactuals, gradients, SHAP, what you name it. So in all these combinations. So does it mean all explanations are wrong? Of course not. I mean, what we're after is a guarantee such that for each data point in my space, the explanation tells me something. I mean, it could very well be possible that there is an explanation that is perfectly meaningful and conveys a lot of information and so on, because maybe the function in this particular part of the space is very simple. Just we cannot guarantee that this is the case until the bank would guarantee us that the function is simple. And then the other thing that many people say when I sort of give this presentation, they say, yeah, sure, maybe you can't guarantee this, but yet my explanations often turn out to be useful. I don't know, I do images and there is in this a doc, and look, the doc is being highlighted. So it seems to be useful. My answer would be yes, again, I mean, there might be many cases where your image explanation reveals the doc, but like playing with like these image explanations, you will have seen many, many examples where it did not reveal the doc, it did something completely stupid. So sure, explanations can be helpful, but you cannot guarantee it. And my point is now, this is very well if we're in some setting where we do code debugging or we have exploratory data analysis. We want to sort of see what our classifier does. There we don't mind if an explanation sometimes is completely meaningless or if we draw even wrong conclusions. But in general, in the AI Act or in a situation where we look at regulation, we simply cannot afford it. So the bank cannot provide an explanation and say, oh, for 40% of all our customers, the explanation might reveal something interesting. For the other 60%, sorry, it's just an explanation. So this simply doesn't work. And this would never, ever, I mean, if it comes to a procedure in front of a court, I mean, this would never go through. So, taking it strictly, as they are currently, explanations are not suitable for regulation purposes. Okay, now this doesn't need to be the end of the story. We can suggest a way forward. And the way forward is explanations do become meaningful if the underlying function gets simple. For example, this is just one mechanism. There are other mechanisms. And as soon as the bank, for example, tells us, look, I use a decision tree and the depth of the tree is only 10, then explanations do become meaningful. So what the bank would need to do to formally get to the regime where an explanation is not useless, completely useless, but at least carries some information, at least a tiny bit, is you need to enrich the explanation. So you need to provide further information about either it could be the function, the simplicity of the function, and other mechanisms exist as well. So something about the stability of the explanation or the robustness of your function in the region where you're asking. So there are many different mechanisms which lead to the fact that explanations are informative. And then once the bank does that, then we can also talk about how informative it is. So of course, like, I don't know, if the bank uses a decision tree which has a very, like, just depth 2, it will be more informative than if the bank says it has depth 100. Probably with 100, we still can't convey much information. But then we're at a place where we can actually discuss. And then we can also discuss whether this explanation is fit for the purpose that we actually might want to pursue with the explanation. My point is, if it's not informative, whatever your purpose is, it's not going to work out. Okay. I think that's the end of my presentation, and now I'm happy for your questions.